Hello, my name is Cmager and I'm a bioengineering student here at SU. I'm also a part of men's tennis team. I've been playing tennis since I was about 6 years old, and throughout my career, I was constantly thinking about different ways I could improve my game. So, looking at the way my body moved while playing and using the data to find areas of improvement was something I got very interested in, and it's how I ended up studying bioengineering. Not just tennis, but all sports are becoming more and more advanced, and that leads to more technology and science being involved with it. Professional athletes are trying to take advantage of every marginal gain they can with the use of devices created by bioengineers. We are able to get a better insight into human physiology and get a useful information that can help us optimize our training process. Example of those devices in tennis are sensors attached to our rackets, with which we can measure the acceleration and based on that determine the types of strokes. Um, Other useful information that we can get from our devices are body temperature, um, glucose levels, and um, heart rate, for example. So a lot of the devices that are made here in the lab are based on some fundamental physics concepts. Some of these can be seen in human physiology. Examples are in respiratory and cardiovascular system. We can see the concept of moving fluids. Um, for example, in respiratory system, when the diaphragm and intercostal muscles contract, it increases the volume of thoracic cavity, allowing the air to flow in. And when the muscles relax, the volume gets decreased and pushes the air out of the lungs. Similar thing can be seen in the case of respiratory system when the heart gets filled up with blood, and when it receives the electrical impulse, it contracts and pushes the blood into circulation. So here I prepared a very simple experiment in order to show the concept of moving fluids. I have some different bulbs and graduated glass pipettes that are filled with colored water. I'm going to be using my fingers to apply pressure to the bulbs, and we're going to be looking at what's happening with the level of the water in the pipette. So if we look at the first example here, let's see what happens when I apply some pressure. So as I'm applying pressure to the bulb, we can see the water level getting higher and higher, which is exactly what we expect. The ratio between the pressure I apply to the bulb and the displacement of the fluid in the pipette is what we call sensitivity. Another important thing we have to consider here is what we call dynamic range, which is the range between the minimal and maximal value of pressure applied that I can still measure. Let's now look what happens when I apply a lot of pressure to the bulb. So here we see that I was squeezing the bulb really hard, and at some point the liquid in the pipette stopped moving. We witnessed the problem of sensitivity. Our device needs more sensitivity, and there are different ways of solving that problem. If we think about it, one thing that we can do is to use a thinner pipette, which is exactly what we did in the second setup here. So if I try and squeeze the bulb again, let's look let's look at what happens. Here we can see that in this second setup, the displacement of the fluid compared to the pressure I apply is a lot bigger, meaning that our setup has a lot more sensitivity compared to the first one. This is due to the thinner pipette here, allowing us to get a better measurement of the pressure applied. Let's think about again what happens when I apply a lot of pressure to the bulb, just like in the first example. So here I squeeze the bulb really hard again, and we see that our device failed. We can see the liquid overflowing, meaning that our dynamic range is not as good as in the first example. So with the increase of sensitivity, we also decreased the dynamic range. Let's think about how to solve this problem now. So to solve the problem of liquid overflowing that we witness in our second setup here, we came up with a solution here in setup 3. So the difference between this device here and the one we just saw is that the bulb here is filled up with the sand that we actually got from the beach volleyball court here on campus. Here we can see the sand used to fill up the bulb. And let's look at what happens when I squeeze the bulb here. Okay, so what we see here is something very unexpected. Instead of liquid moving up, just like in the previous examples, we can see the water level dropping in the pipette. This happens due to the physics phenomena called dilatancy, which happens due to the shear forces applied to the sand particles. So when I squeeze the bulb, the volume between the sand particles gets larger, allowing the liquid to fill up the bulb, and consequently lowering the water level in the pipette. So by doing that, we basically solve the problem of liquid overflowing, and we can apply as much pressure as we want, and our device won't fail. Now, that was just a very simplified example of problem solving we do here in our labs. We can think about applying something like that to an actual medical device. We can think about miniaturizing the setup here and using it in the field of microfluidics, for example. We did something like that with our intraocular pressure lens that was created here. To show you an example of that, I have it right here, and we can see just how small it is. And we can imagine the complexity that comes with applying something seen here to a device of the size of a contact lens. So this was just a quick demonstration of the process we do when designing a device in bioengineering. We've seen that some very fundamental physics concepts can be applied to actual medical devices. So I hope you enjoyed it, and thanks for watching.